we will discuss the white strong-arm latch itself and understand it's quite handy owing to its compatibility with the following digital CMOS logic. However, we never discuss how the compatibility could be done. Also, the extra circuitry will limit the following digital timing, and we need to watch out carefully. Therefore, we need to know why the strong-arm latch would need an optimized RS latch to meet the digital timing at the block interface. Before that, think about the reset images for 5 seconds. Bingo! Last time, we added the reset devices into the strong-arm latch to remove the memory of the last resolved state, such that we could flip over the output polarity if the input was sampled at an opposite polarity. Do you remember the strong-arm's output would be pulled up to VDD during the half of the clock cycle at a low level? Therefore, it's not the right data information, and we need to interpret the output correctly for the following logic. What can we do? Think about another latch, which could keep the previous states while both inputs are high for 5 seconds. Correct. From Digital Logic 101, you should remember the truth table of the SR Latch may latch to the previous state if both inputs are large 0. Also, the output Q will follow the input S, and the output Q bar will follow the input R, while Q bar is an inversion of Q. Therefore, this no-gate based SR latch won't meet our needs, since the strong-arm latch requires to latch to the previous state if both inputs are large 1, not 0. Fortunately, it's very straightforward to invert the inputs, which are the output of the strong-arm latch, by replacing the no-gate with the NAND gate-based SR latch. Reviewing the truth table of the NAND gate-based SR latch one more time, and you will find the values match what we need very well. First, both 0 will force both Q and Q bar outputs to be 1. Even though this is a forbidden state, both differential output of the strong-arm latch are never to be 0 at the same time, which should be fine. Second, the Q will follow the R bar, and Q bar will follow the S bar. Therefore, it's easy to measure the proper polarity. Lastly, both ones from the output of the strong-arm latch would be don't care inputs at the NAND gate inputs, and the SR latch will keep latching at the previous state. Now, we get the logic right, but you need to rethink the gate delay images for 5 seconds. Correct. Even though the truth table shows the output and input mapping relationship, the digital gates would have a gate delay, which would toggle one by one sequentially. Therefore, we must trace the delay carefully to make sure the delay don't cause any timing variation. Let me show a simple timing image, and you could realize the delay issue here. First, start with the S bar equals 1 equals Q bar, and R bar equals 0 equals Q. Then S bar equals R bar equals 1 during the strong arm's reset phase. Second, if the strong arm sends an opposite polarity from the previous sample, the R bar will toggle from 1 to 0, while the S bar keeps 1, such that the Q equals 1, and then Q bar toggle from 0 to 1. Third, the S bar was 1, and the Q will toggle from 1 to 0, because the Q bar toggle from 0 to 1. Therefore, it's obvious the Q has 1 gate delay of Q bar, which may delay the data transition age too much to meet the following flip-flop setup time. So, what should we do? Think about the pull-down images for 5 seconds. Bingo! The output Q's pull-down event was waiting for the output Q bar's transition. So, we could add a pull-down path to speed up the pull-down event, while one of the input would be 0, and the other output would be 1. and pull the other output to be 0. For example, the Q bar was toggled from 0 to 1 to make the Q to toggle from 1 to 0. We've known this pattern, so we could just pull the Q down without waiting for the Q bar, but noisy from the R bar toggle to 0, which should set the Q bar to be 1. Therefore, adding the R bar with the pull down and an inverter to pull the Q was the intention. Similarly, to apply on the S bar and Q bar bridges. As you can see, with this improved SR latch, the transitions of both Q and Q bar align with a less delay for the following flip-flop to extend the data's arrival time and meet the setup time requirement easily. Is this good enough? Think about the image of the clock to Q delay of the sampler for 5 seconds. Right, the sampler would be a strong latch with the SR latch. Therefore, the clock to Q delay would be the sum of both gate delay. Even though we briefly discussed how the time constant of the regeneration time in the why strong up latch video, and adding an optimized SR latch now, the whole clock to Q delay might still need to be reduced further. But how? Let's go through the clock to Q delay of the strong arm latch and see if there are any places we can improve. Alright, let's start with the reset phase. Wait a second, you may be wondering if CC is presenting the right one. The reset phase is doing nothing without any data information and latches to the previous state at the SR latch output. But if the reset phase is slow, and the residual memory will degrade the clock to Q delay of the next sampling and regeneration phase. Therefore, we must check the differential signals at SY and PQ are nearly 0 during the reset phase. If not, we must increase the size of the M789 to make the reset stronger. But don't oversize those reset devices. Otherwise, the capacitance will load the regeneration device and increase the clock to Q delay. What's the next phase? Yes, sampling or amplification phase. In this phase, the tail device switch M10 is turned on, and the input differential pair amplifies the input tiny differential signal. Since the common mode current sets the gain and speed by dropping the output at PQ, we need to make sure the input common mode voltage was the optimal level, which can be simulated or verified. Similarly, the device size of the M12 should also have an optimal size to get the optimal GM to discharge the CP and CQ quickly, which also implies the capacitance at the P and Q should be minimized without self-loading from M12. As long as the voltage at PQ drops below VDD minus 1 threshold voltage, the regeneration MOS pair will turn on. Great. Then entering the regeneration phase 1 with the M34 to drop the VR voltage further until the M56 are turned on. In this phase, all the capacitance at the X, Y, P, and Q must be minimized. That emphasize one more time that the reset devices cannot be as big as possible. Just make sure the reset was good enough instead. Lastly, as long as the M56 turn on, the final regeneration phase will finish the whole positive feedback around these transistors and eventually bring one output back to the VDD while allowing the other one to fall to 0. Even though the precise time constant is set here, you should have an intuitive way of minimizing all the capacitance and maximizing the GM here. The reset of the design work is to size properly in your design process now. Here are a summarized image of why the strong arm latch would need an optimized RS latch to meet the digital timing and the block interface. First, During the strong arms reset phase, the outputs are not valid data and must be converted through the SR latch for sure. But the SR latch's falling transition must follow the rising transition, which adds extra unnecessary delay. With a simple pull-down device and the right polarity, both rising and falling transition will match properly and shorten the gate delay. This is a soft reminder of the sampler's clock-to-Q delay is not just strong arms delay, but also the SR latch delay. Therefore, the improved SR latch does help a lot to speed up the timing margin. To make sure to optimize the whole sampler delay, we need to revisit the strong arms delay. First, the reset phase must be complete with initial residual differential voltage at the X, Y, and QP. Second, optimize the input common mode with the input size of the differential pair is a must. Third, keep the capacitance at the XY and PQ as small as possible by making the reset device small enough and reducing the parasitic capacitance as much as possible. Lastly, maximizing the GM of the regeneration device, but still need to keep the capacitance as little as possible at the output. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.